Our next speaker is Christian Elsholtz from Graz, who will speak on Fermat's last theorem, implying that there are infinitely many primes. Who would have guessed?
Yes, thank you, Mel, and thank you all the organizers for organizing this wonderful conference. I think it's growing very quickly over the last years, and this, of course, is very good for us. I don't have to travel to New York. Thank you very much. Actually, I'm switching off the video because of the internet bandwidth, and it's also irritating myself. All right, so Mel already said one would have guessed. I'm not sure if anybody would have guessed that it's a very unusual title, and of course you would like to prove the opposite. So just imagine you live in a world with finitely many primes, and then think about the consequences. And well, if you're a number theorist, at least in analytic number theory, you see that most of analytic number theory just goes away. Everything that has to do with primes and theta functions is about counting, and it just goes away. And you will see very soon that also a big part of algebraic number theory goes away, namely Fermat's last theorem. And also, there are quite a few combinatorially interesting theorems which would imply Euclid's theorem, which one would not have guessed. And so the world would be very different. Yeah, also in additive combinatorics, for example, Roth-Semerady type theorems are very, very important. So they are also involved to this, and they would also not exist. So actually, if you want to read the paper online right now, I don't mind. It's, in my opinion, very nice to read, enjoyable. It's more a fun paper than deep research, I admit. And just, if you don't want to type in this DOE number, just Google for monthly Elsholtz and Fermat. You find the paper on the webpage of the monthly. So just to give a few keywords of the proof and what I will talk about in the next few minutes. So we really start with the title, Fermat's last theorem, and Shus Theorem of combinatorics implies there exist infinitely many primes. And this is certainly not a kind of easy proof in this sense, but we will have some variations. So coming out of seeing what's going on in the background, we actually find a new proof of Euclid's theorem, which is quite simple. And we will also involve a couple of other big theorems like Faltings, Roth, etc. And then we move from number theory more or less a bit to combinatorics. So we increase the combinatorial input, and then we will see that we can reduce the number theoretic input a lot. So we come to new proofs, which are almost combinatorial. And at the very end, I will have some informal discussion on maybe we should know something about the lower bound complexity of Fermat's last theorem. I mean, everybody wants to simplify the proof, and maybe you can't make it really easy. And Euclid's theorem is kind of certainly a very, very low threshold, actually. So the inspiration comes from two papers by Alpoga and by Granville. Alpoga introduced to the subject that you look at the exponents of a prime factorization, you look at combinatorial patterns in the exponents. He used van der Waals' theorem and came up with a completely new type of proof of Euclid's theory. And then Granville looked at this and he employed a theorem by Fermat, namely that there are no four squares in arithmetic progressions. And from this, he could say, well, you don't need the long progressions of van der Waals, and he gave a new proof. And when I looked at this, I saw, well, actually, you can go further. You can take no three progressions, for example, of cubes. And so I saw you can apply Fermat's last theorem, which doesn't make the proof easier, but in my opinion, it makes the proof more funny. So there was some unexpected media coverage, or modern media coverage, so to say. Tim Gowers tweeted on his Twitter account with 13 tweets, more or less giving the core of the proof. And so, well, yeah, he starts with, it's always amusing to read proofs that use massive sledgehammers to crack nuts. Yes, that's what's the paper about. And also when it appeared actually in the monthly, the MAA and the publishers had kind of a Twitter announcement, which they do not usually have about research papers. It just seemed to be an interesting paper. Also, the publisher made it open access. I didn't ask for it. I didn't pay for it. It just happened. Okay, back to maths. So Shus theorem is probably known in this conference, CANT. So it's certainly one of the first theorems in combinatorial number theory. So if you fix a number of colors, say t, then there exists an interval of size from 1 to st, so that if you color the integers in this finite interval with the t distinct colors, then there is always a monochromatic solution a plus b equals c. And this st is not super large, it's t factorial times e. And actually, Schur's motivation comes from Fermat's last theorem. So at that time, people hoped to prove Fermat's last theorem by proving that there are lots of modular obstructions. And if you can compose many modular obstructions, you might find a proof. But Dixon already proved there are no obstructions. And Schur gave a simpler proof and a more general proof. And this is what this lemma is. So formally, I'm going to prove the following, and I'm phrasing it kind of carefully. So n is at least 3, and the FLT of n is just a logical statement. There are no solutions of the Fermat equation, x to the n plus y to the n equals z to the n, and positive integers x, y, z. And then I'm going to prove if FLT of n is true, and if you assume Schur's theorem is true, then this implies there exist infinitely many primes. The reason why I'm stating it in this way is that I'm not claiming this is necessarily a new proof of Euclid's theorem. Namely, if it were a new proof, you would need to check whether your proof of Fermat's last theorem possibly implies or possibly uses infinitely many primes in some way. And this is actually what happens. If you look at Weyl's proof, which is not easy to read, of course, but you find somewhere he uses primes by Chepotarev's theorem. So he uses strong results on there exist infinitely many primes. But anyway, if you read the proofs for small exponents like 3, 4, and 5, then it seems to me that one is not needing the existence of infinitely many primes. So for the exponent 4, for example, the proof goes roughly like you know the parameterization of Pythagorean triples and use that a couple of times, and maybe some GCD conditions or something. And in my opinion, I didn't check it super carefully, but I believe it doesn't use the existence of infinitely many primes. So for small exponent, it might actually be a new proof because the existing proofs don't use Euclid's theorem. Okay, anyway, even if for the general integer n, one needs Correlly, Weyl's proof Correlly needs Euclid is still the formal statement FLT of any fixed number n, at least 3, and Schur implies Euclid, of course, stays true. Right, here's the proof. Okay, suppose there exist finitely many primes, and you write then an integer m in the standard prime factorization, and now you split the exponent ei into a factor n times qi plus a remainder, and the remainder is then small between 0 and n minus 1. So if you then reorder the factors, you have all the factors which have at least nth powers, a multiple of nth powers. So the first factor is an nth power, and then this is the remainder factor where the Ra are smaller than n. Right, so this gives us, so the last factor is considered to kind of have the color information. So you have k values of these Ri, and so you just have n to the k, for the Ri you have n choices, and you can do that k times. So you have n to the k distinct color vectors. Now the vector is just say Ti and Ri is the same essentially. So the vector is just the Ri's. Right, so every number m gets a color according to these remainders Ri. And now by Schur's theorem, there exists a monochromatic triple ABC, which has the same color factor. This is the color factor. It's the same for all of these 3 numbers, a plus b equals c. So this means actually you can cancel this factor. All of a, b, and c have the same factors. You can cancel it. And so after cancellation, you come to na plus n. Yeah, so na was this nth power factor from the third line here. So na plus nb equals nc, and these are just nth powers. And this contradicts, of course, your statement that FLT of n is proven. Whatever the way of proving was doesn't matter. So I said, I suppose this is proven. Okay, so this is the proof actually. Okay, so I will now have some variants of the proof. If you study this weighted Fermat equation, xn plus yn equals 2 times z to the n, which actually is also proved to contain non-trivial examples by Damon and Merel. And the reason why this is a bit interesting is, so these solutions of this equation would be in an arithmetic progression. So to say there are no such solution means there are no 3 nth powers in an arithmetic progression. And actually then when thinking about this, I came up with the following. Okay, suppose we go, so we are in a world with just finitely many prime factors. Suppose there are k prime factors at most. And then the set of nth powers is a positive proportion of all integers. That's a bit surprising because the number of powers up to n is, say up to capital N is n to the 1 over little n. So, but in the world with finitely many primes, they're just, it's a positive proportion. Yeah. So here's actually formally the proof. So I'm dividing a lower bound approximation of the nth powers divided by an upper bound approximation of all integers in the interval from 1 to capital N. And I count in terms of these exponents EI. So to give an upper bound, the exponents EI are at most log n over log pi I. And then you take the product. So this product gives you an upper bound on the number of nth powers. Sorry, on the number of integers, and the lower bound on the number of nth powers. So here we assume that each of the factors is at most, say, the average geometric share of n to the 1 over k, and then you take the logs, and you see this factor, this product here is a lower bound for the number of nth powers, and you take the proportion lower bound of the nth powers divided by upper bound of the whole interval, and this comes up to be a constant. Yeah, n and k is constant, and c is another constant coming from rounding errors or something like this. So this is a constant. So there is a positive proportion delta, and the nth powers are positive, have at least a positive proportion. And then, of course, you can use other type of theorems. You can replace Shus Theorem by Roth Theorem, and this directly gives you a non-trivial arithmetic progression. And therefore, it also gives you a new type of proof of Euclid's theory. But you can also get now a much easier new elementary proof of Euclid, avoiding Fermat and all that. So the lemma says, well, the nth powers are positive proportion, but then of course you do know that the nth powers have a counting function of capital N to the 1 over n. And then you know for large n, this is a contradiction. Yeah? So I believe this proof is new. And if you have a new proof and want to check if it's really new, so what I would recommend, there is a very, very nice survey by Mestrovich. It has kind of hundreds of proofs and ordered in a very reasonable way and giving all the references. And I believe this proof actually is new. And this proof, of course, is quite simple. Right, so some more discussion. So if you know more on combinatorics, you can actually reduce the number theory. So for example, there's a paper by Frankel, Graham, and Rödel, which says, well, you do not only get one monochromatic solution in Shus theorem, but actually you get lots of monochromatic solutions. You get quadratically many. But this contradicts the number theoretic estimates. So on the one hand side, you could say by Falting's theorem, there are very few solutions only. And by another, actually much easier argument than Falting's, you could factor the left-hand side. So if n is odd, you can actually give such a factorization is divisible by x plus y, or I do that here explicitly for cubes. Yeah, so x plus y is an explicit factor. And then, of course, you know by estimates on the divisors, well, they're at most square root of your bound, square root of the size of your interval, many factors. And if you combine that, just the number theory tells you there cannot be quadratically many solutions. So combinatorics tells you there will be quadratically many solutions. Number theory tells you there will be less than quadratically many solutions. And the same is also true for the equation I mentioned earlier with this arithmetic progression. Right, so I'm now going to use some deep combinatorial theorems, and then I'm reducing them step by step. So there is a famous theorem by Hindman. So if you have t coloring, t is the number of colors, each of the integers gets one of the values from 1 to t. And then you do have an infinite sequence A of elements, A1, A2, etc. And then you take all finite subset sums. And there are infinitely many finite subset sums. And then there exists a monochromatic A such that all these infinitely many finite subset sums are monochromatic. And this is non-trivial. So the finite case is much easier, but the infinite case is hard. So anyway, Hindmans theorem implies Euclid's theorem, and the proof is very similar to what I did before. And if you like, you can look it up in the paper. But then if you look at the proof, you see, well, most of the stuff from Hindmans theorem you don't actually need. For example, you only need sums of 2 elements. And then more or less you think, well, in terms of graph theory, maybe you can reduce that. So you can use an infinite Ramsey type lemma. So if you have a finite set X, and you color this with finitely many colors, and then there exists some infinite subset M of X, such that all the subsets of M of a fixed size have the same color. And if the size is 2, this is just the case of graphs. So this then says if you have well, infinitely many vertices, there is some, and all of the vertices are connected and colored, the edges are colored with finitely many colors. And then there is an infinitely many subgraph of this infinite graph. And such that in this infinite subgraph, all of the edges are monochromatic. So again, this implies Euclid's theorem. And if you look more carefully, you see this is still too much. You don't need it. So what I'm now going to do is, okay, on the next slide, I will introduce a so-called K2 infinity lemma, which is kind of a very special subcase of the previous Ramsey type lemma. But anyway, then I'm reducing the number theory heavily. And so what I use from number theory is the following trivial results. So the gaps between nth powers are increasing if n is at least 2. And the proof is actually in the last line, xn minus y to the n if x is larger than y. Of course, you do some trivial binomial expansion, and you see this tends to infinity. So this is, of course, trivial. Then you use also completely trivial that you can add and multiply. So p, w, and v here are integers, so you can just use the normal the normal rules, and also for factors. And this is the ingredients I use from number theory. And actually, so here for the number 1, if you fix this gap, if you fix the d, it implies that there are just finitely many solutions of d written as a gap between nth powers. Yeah, this is the consequence of the gaps are increasing. Right. So what do I use on the combinatorial side? This K2 infinity lemma. This says the following. So if you color this as before, then you find a subgraph of the following type, a so-called bipartite subgraph. It has 2 parts, namely one part contains of just 2 vertices, v1, v2. And the second part is actually infinitely large. And if you now combine all the v's, or the 2 v's are connected to all the other w's. And this is monochromatic. And this is, of course, a much easier case than what I said before, that all the combinations between, you have infinitely many vertices and all of them are connected in a monochromatic way. So I give you a graph, a picture of this graph. Say you have 2 vertices on the left-hand side and then infinitely many on the right-hand side. But here in particular, you are not connecting the many edges W. So W1 and W2, you don't care about the number. So that's why it's much less information than in this infinite Ramsey theorem I mentioned a moment before. And so actually I'm proving this lemma, and this is the page more or less, but actually I'm proving this rather with a picture. So do the following. So just take, so t is the number of colors. So take t plus 1 special values, a1, a2, up to at plus 1. And then on the right-hand side, you want to build up these infinite set x. And on the left-hand side, you want to choose 2 suitable values. And so from this A1 is connected to all of the X on the right-hand side, but there's at least one of the colors which must occur infinitely often. And you order it in such a way that, say, this is written at the top. So the top few elements are connected to this A1, and the color, say, is C1. And then you start from the right-hand side, and you want to connect. So all of them, of course, are connected to A2, but maybe not in the same color. Anyway, there exists some color, which we call C2, and which occurs infinitely often. If C1 equals C2, if the color is the same, then you have your pattern which you want. But in the general case, this is not the case. So, but then you go on. So then you choose, you started with a set X on the right-hand side, which are all connected to A1 with color C1. And now you have a subset of the set X, say, let's call it X2, which are also monochromatically connected to A2, but say in a second color C2. And you go on like this. You take a subset of X1 and then X2 and then X3. And each of them are, again, monochromatically connected to, say, A3, A4, but maybe in a different color. But if you do this T+1 times, you realize by the pigeonhole principle, you have just T colors. So there must exist two indices where you actually used exactly the same color. And you choose these two indices, then AI and AJ, and they are connected monochromatically to the right-hand side to these sets XJ with the right index then. So this is kind of really easy, say, set theoretic. I wouldn't even call it combinatorics. So this K2 infinity lemma and the trivial number theory I mentioned before implies Euclid's theorem. And again, here's the proof. So it's very similar to before. So n is at least 2. You have k primes. Integers are written in the standard way of pi to an nth exponent plus a remainder. The coloring actually is defined by, now if you have an edge, mi, mj, and you take the sum mi plus mj and do the prime factorization as above, and this sum defines the color of this edge. Right, and now you now by the K2 infinity lemma that this has this special vertices v1 and v2, and these are connected on the right-hand side to infinitely many edges in a monochromatic way. Monochromatic means all of these sums then have the same pattern for the exponents. And now you multiply everything by this factor capital P, which is the prime, to the n minus RA. And this minus RA just inverts the color information. So after multiplication, all of this got an nth power. So if you had VI plus WJ with some coloring multiplied with P, now the right-hand side is an nth power. Say the nth power, call it Zij to the n, and you do that 2 times. And then you take the difference. And the difference on the right-hand side is a constant, P times V2 minus V1. And on the left-hand side, it's a difference between nth powers. And I told you before in the lemma, if you have a fixed distance, you just have finitely many ways of writing it as a difference of nth powers, because trivially the gaps are increasing. But now on the left-hand side, you have this parameter j. So, and j comes from this K2 infinity lemma. There are infinitely many j's. So this gives you a contradiction. So this is, I think, a really kind of graph theoretically inspired proof using reducing the number theory a lot. So I started with Hindmans Theorem on the combinatoric side, which was way overkill, and then I reduced this information. So the K2 infinity lemma, which has a relatively simple proof, I reduced the number theory a lot. Right, so if you, okay, so this is just a summary of the type of results you could prove. So, but I wanted to come to a last page, say something about the minimal complexity of Fermat's last theorem. I cannot really say much about it, but maybe one should study it more. I mean, if one really wants to simplify Fermat, maybe one should come from the other side and say it cannot be easier than the following. So here I say, well, if you combine Fermat's last theorem, say with a fixed exponent and Shus theorem, then it cannot be easier than Euclid's theorem. Actually, here this Euler's theorem is here misprint actually. And if you remember in computer science, people have a lot of hierarchy of complexity classes of certain algorithms. And in logic, you often say, well, this theorem can only be proved if you have the following axiom. And so, yeah, what can we say about what's the minimal complexity of proving Fermat's last theorem? I mean, just saying Euclid, of course, that's a very low threshold. But if we could say it needs the following type of theorem, and this alone needs at least 10 pages, maybe that would be an interesting statement. Thank you very much.
Thank you, Christian. Are there any questions for our speaker? If not, then I thank Christian again. And the next talk will be in 3 minutes.
Thank you very much.